Good evening, chemists. Great to see you guys again. Last time we were studying supersaturation, and hopefully some of you got to either do or watch the experiment of hot ice. And today we're going to learn about concentration of solutions. Today's lesson is 8.5, concentration of solutions. So I'm going to share that with you. Great. And we'll start off with a question of the day here. I've got a glass. You're going to guess, is this solution here unsaturated, saturated, or supersaturated? We'll see if you can tell by looking at it. What test could you do to try to figure it out? Great idea. Let's add a little bit more solute and see what happens. All right. Doesn't look any different, huh? So we're going to guess that it was unsaturated. We added some more solute. It also dissolved. So we still can't see anything in there. Awesome. So on a solubility curve, where would this be? Under the line, right on the line, or above the line? Well, if it's unsaturated, that would be somewhere below the line down here. Awesome. So today we're going to do a little check-in about how the mini lab went, go over homework, have our lesson on molarity, and practice with homework 14. And again, our aim today is 8.5. How do we measure concentration of solutions? So this reference table is the one we've been using, and it's here again for your reference. It's also in the PowerPoint. Let's take a look back at homework 13. So question 1 said a solution contains 14 grams of potassium chloride and 100 grams of water at 40 degrees Celsius. What is the minimum amount of potassium chloride that must be added to make this a saturated solution? So that's 14 grams of potassium chloride, 40 degrees Celsius. Let's look at table G. So we're looking here at potassium chloride. At 40 degrees Celsius, it looks like you need about 39 grams of potassium chloride for it to be saturated. But they said you already have 14 grams. So if you need 39 grams for it to be saturated, you already have 14. 39 minus 14 is 25. So I got that one. For 3, which one is supersaturated at 50 degrees Celsius? If we look back here, 50 degrees, NH4Cl, ammonium chloride, it looks like you'd need about 52 degrees to be saturated. So 52 grams to be saturated. 58 grams would be supersaturated. On the back, looking at the same reference table, we're trying to figure out which of these trials looks like it was an error. As you look, as the temperature increases, the solubility of this solid, potassium nitrate, gets higher and higher and higher. That makes sense, right? The more you heat the water, the more the water can hold. Until you get to this last trial where all of a sudden it can't hold as much. That seems to be an error. It does not fit the pattern. So that would be trial 4. And then in number 6, we've got an unsaturated solution made by completely dissolving 20 grams of sodium nitrate in 100 grams of water at 20 degrees Celsius. In part B, it says, determine the minimum mass of sodium nitrate that must be added to this unsaturated solution to make a saturated solution at 20 degrees Celsius. Well, if I look back at table G, we're looking for 20 grams sodium nitrate, 20 degrees Celsius. Looks like at 20 degrees Celsius, sodium nitrate, you need about 88 grams to be saturated. They said they already put in 20 grams. That's definitely not saturated. So to get all the way up to the line there, you'd need about 68 more grams. So that's the answer. So for the live session, I'm really curious to hear how the mini lab went for you, either watching or doing the experiment. And if you tried it at home, please let me know. Maybe I could even give you extra credit if you got some photos of that. Thanks for giving that a try, you guys. And if you still want to try it, you're still welcome to. And you're still welcome to get the extra credit if you want to take a photo or something and show me that you tried it at home. And here are the post-lab questions. So today's aim is 8.5. How do we measure concentration of solutions? So maybe some of you have done this in the frozen aisle of the grocery store. You can buy juice from concentrate. And some of you might not be familiar with this, but it comes in a can, and if you just eat it straight, it's super delicious, but super intense flavor. Because you're meant to add it to a big pitcher of water with 3 cans full of water. So then you mix the juice into the water and it makes actual regular juice. So that's called juice from concentrate. So how do you do it? That's how you do it. What would you do if you wanted to make it taste sweeter, more juicy? That's right, you'd add less water than they tell you to. Fun trick. What if you were going to give the juice to a baby who shouldn't have too much sugar? What would you do? That's right, you'd add more water than it directs. So this is the same exact concept of concentration for a solution. The way we measure it in chemistry is usually not how many cans of concentrate to how many cans of water, but in molarity. Molarity is a measure of concentration of solutions. And if you're thinking that has to do with moles, you're right, it does. So in this picture, the more concentrated solutions are on the right, those are going to have higher molarity. And then over here, we've got the more dilute solutions. Those are going to have a lot lower molarity. So a dilute solution has low molarity, while a very concentrated solution has a higher molarity. All right, so we've got 2 pictures here. Take a moment and think, which one do you think has a higher molarity? Right, well, they've got the same number of dots, but one has way less volume, so it's way more concentrated. That means the little one here is going to have higher molarity, more concentrated. Or another way to think about that would be more stuff per amount of water. And that is actually the equation we can use to measure it quantitatively. Molarity is how many moles of stuff did you put into it, solute, divided by how big is it, or how many liters of solution. And this is also on the back of your reference tables on that list of equations on table T in the very back. You might have noticed it before when we were studying moles and wondered what it was about. So for instance, say I'm making a solution. I put 6 moles of sodium hydroxide into a solution, and the volume of the solution is 3 liters. I've got 3 liters of water. So what is the molarity? Well, molarity is, let's see if this guy works here. Molarity equals moles per liter. So that'll be 6 moles divided by 3 liters equals 2 molar. Awesome. So we call that a 2 molar solution. Yeah. Here's a little joke for you. A 5 molar solution. Get it? It's teeth, molars. Okay. So why does this matter? Well, say you're cleaning your house. Would you use an acid? Scary. No, that seems like a bad idea, right? Well, actually, a lot of people do. Many cleaners have acids in them, like vinegar. It's just that they're very, very dilute. So often, the difference between safe and helpful and poison is actually concentration. That's very true in medicine, right? There's a reason you take a certain amount of medicine. Super concentrated medicine is poisonous, but the exact right amount is very helpful. So concentration is super important. Here's an example with the molarity equation. What is the molarity of an H2SO4 solution? 0.25 liters of the solution contains 0.75 moles of H2SO4. So I'll give you a moment to think about that. Okay, so here's our equation again. So which number goes in the numerator? Yeah, 0.75. So that's the solute. And then what goes on the bottom? That's right, 0.25 liters. So that'll be 3 moles per liter, or big M, capital M, is for molarity. Awesome. All right, let's try this example. What is the molarity of a potassium fluoride aqueous solution containing 116 grams of potassium fluoride solid and 1 liter of solution? Ah, look out. What's the problem? Yeah, it's in grams. And for molarity, we want, of course, moles, not grams. You guys remember how to do this? Okay, let's look at the gram formula mass of potassium fluoride to figure out how many moles 116 grams is. Well, potassium weighs 39, fluorine weighs 19, so that makes 58, right? So 58 grams per mole. Oops, hey. 58 grams per mole. So we've got, that's the gram formula mass, we've got 116 grams. We want to know how many moles is that? So if you have a unit that has to go, where do you put that unit? Down below. So we'll put 58 grams down here. Have a unit that you love, where do you put that unit? Up above. So that makes, that's 2, right? Just double checking on my handy calculator. Thanks. Okay, 2 moles. Okay, now we're almost done, but remember our molarity equation. Molarity equals moles per liter. So that's 2 moles over how many liters? Oh, 1. How convenient. 2 over 1 equals 2. Awesome. So not actually that scary, right? Just got to remember molarity is in moles. So if it's in grams or something funny, you just want to switch it to moles. Usually the only 2 options are grams or moles, so that's convenient. But if the volume were in milliliters or something, you'd want to change that to liters, because molarity is moles per liter. All right, what if you know only the molarity of a solution? You also know the volume, you know how big it is. Is there any way to tell how many moles of solute were put into that solution? Why, yes, of course there are. Equations are just so super magical. You can move them around, right? So we're going to do an example of that with this example, which tells us the molarity and the volume, but not the moles. That's what we're solving for. So one way to do that is just use your algebra skills to solve for x. So you would just say 3 molar equals x moles over 4 liters. And then liters times molarity would give you moles. If that makes you queasy, there's also this wonderful trick called the magic triangle. The magic triangle works like this. If you haven't used this before, it's pretty fun. So molarity equals moles divided by liters. That means if you put them in this triangle like this line means divide by, and this line means multiply by. Whichever thing you're looking for, you cover it up and see what's left. So if I were looking for molarity, I'd cover up M. What's left? Moles divided by liters. That's this equation. Great. What about in this case, I want moles. So you cover up moles. What's left? Molarity times liters. So that's 3 times 4. Say you wanted liters, volume. You cover up liters. What's left? Moles divided by molarity. It's just another fun way to do algebra. So in this case, either way, we're going to end up with multiplying both sides by 4. So that equals 12 moles. Yay. Yay, math. All right, so I'd like you guys to try it. You can use the magic triangle or algebra, whatever you like. You need 2 moles of sodium hydroxide, and you have a solution. It's got a molarity of 0.5 molar. So how many liters of this solution do you need? All right, first we will use the magic triangle. Going to cover up liters. That means I'm left with moles divided by molarity. So 2 moles divided by 0.5 equals 4 liters. All right, let's also do it using algebra. So molarity equals moles per liter. We'll put in 0.5 for molarity, 2 for moles. Solve for x will be liters. So I'll multiply both sides by x. Then divide both sides by 0.5 to get the x by itself. X equals 2 over 0.5. Same thing, equals 4. Yay! Okay. So this last example is a real challenge. I'd like you to definitely pause the video, read through this, try it, and then you can push play when you're ready for the solution. So this is a graph showing solubility of oxygen in water versus temperature. X-axis is temperature, y-axis is mass of dissolved oxygen in milligrams in 1,000 grams of water. So the first thing you might notice is this line goes down. Well, that means the warmer the water, the harder it is for it to hold the oxygen gas. It's because oxygen's a gas, right? So that makes sense. Okay, so A student determines that 9.8 milligrams of O2 dissolve in 1,000 grams of water at 20 degrees Celsius. In terms of saturation, what type of solution is this? So let's look at this. We've got 20 degrees Celsius, 9.8 milligrams. So these lines go up by 2s, it looks like. 5, 7, 9, oh wait, no, 5, 6, 7, oh, they go up by 1s. Oops, my bad. Okay, so 5, 6, 7, 8, 9. They said 9.8 milligrams. So that's like right here. So what type of solution is this in terms of saturation? Unsaturated, saturated, or supersaturated? That's right, supersaturated. Yay, okay. Now it says, explain in terms of molecular polarity why oxygen has low solubility in water. All right, oxygen is O2. What do you think, symmetrical or not? Yes, symmetrical, meaning it is non-polar. Okay, non-polar. How about water? Symmetrical or not? No, it's polar. So do non-polar things mix well with polar things? No. Oxygen has low solubility in water because, oops, it is non-polar. And water is polar. Okay, last question is the hardest. What is the molarity of this solution at 20 degrees Celsius? All right, we know the equation is moles per liter, but we have neither moles nor liters. For O2, we've got milligrams. Where did it go? Yeah, up here. 9.8 milligrams is not moles. And for liters, we've actually got milliliters. It's dissolved in, or grams, it's dissolved in 1,000 grams of water. Now I put this little helpful hint for you that 1 gram of water equals 1 milliliter. So that means we've got, I'm going to write up here, for the denominator of the equation, we do know, hey, come here, that it's 1,000 milliliters, which is 1 liter. So that's helpful. But what the heck, how many moles is 9.8 milligrams? All right, so first I'm just going to change that milligrams to grams. Hey, that was an 8. Okay, so I'll say 8. 10 to the 3. Milligrams. Oh, sorry. How do I erase? Oh, okay. 10 to the 3 goes up. 10 to the negative 3 goes up here. Milligrams is 1 gram. Okay. Oops. This is so messed up and very ugly now. Okay, I'm gonna start over. 9.8 milligrams. I should ask you guys, then I get it right. If you have a unit that has to go, where do you put that unit? Down below. I want to turn it into grams. Okay, so there's 1,000 milligrams in a gram, or you could say a 10 to the negative 3 gram is 1 milligram. All right, if you have a unit that has to go, where does that unit go? Down below. And now I'll turn it into moles. So for oxygen, O2, each oxygen atom is 16, so that would be 32 grams per mole. So we'll do 9.8 times 1,000 times, oops, divided by is 306 moles. Oops, I did times 1,000 instead of times 10 to the negative 3. Wow, divided by 1,000. Now divided by 32. Ooh, that's hardly any moles. 3.1 times 10 to the negative 4. So I'll put that over here. Does it make sense that it would be a small number? Yeah, because oxygen doesn't dissolve very well in water. And of course, that divided by 1 just equals itself. So it'll be 3.1 times 10 to the negative 4. Awesome. Thank you guys so much. Great work. Homework tonight is homework number 14, and that's on Go Formative. Let me know if you have any questions.